Right, let's dive in. We're about to uncover a kind of hidden language, a mathematical structure that, believe it or not, secretly governs our entire universe, from the simplest shapes you can imagine to the most fundamental laws of nature.
So, to get us started, here's a little puzzle for you. What could a simple triangle, a spinning frisbee, and the whole universe possibly have in common? It sounds a little weird, I know, but the answer reveals something truly elegant about the world we live in.
The key to solving that puzzle starts with a concept we all kind of get intuitively: symmetry. It's about balance, things looking the same even after you move them around. But it turns out there are some very precise rules hiding just under the surface. Now, in the world of mathematics, these rules of symmetry get bundled up into this really powerful idea called a group. You can think of a group as the complete collection of all the moves, all the twists, flips, and turns you can do to an object where it ends up looking exactly like it did when you started. So let's take a perfect equilateral triangle. It turns out there are exactly 6 ways to mess with it and have it look unchanged. We can rotate it by 120 degrees or 240. And of course, a 360-degree spin just brings it right back home. Then you've got 3 different ways you can flip it. That's it. Those 6 moves make up its complete group. Now, here's the crucial thing to notice. These symmetries are discrete. You can literally count them on your fingers. There are 6 separate, distinct actions. They're like steps on a staircase. But what happens when the symmetries aren't separate steps at all? And that question takes us away from the rigid, step-by-step world of the triangle to something, well, a lot more fluid, something with a whole different kind of symmetry. Okay, check out this difference. A triangle has its 6 specific moves, right? But now think about a spinning frisbee. It looks the same after any amount of rotation. It doesn't matter if you turn it a tiny 1.5 degrees or a big 150 degrees. It's still a perfect circle. It's always symmetrical. So what does this mean? It means the frisbee has an infinite number of symmetries. It's not a handful of separate steps anymore. It's this smooth, unbroken flow of transformations. And that's what mathematicians call a continuous group. And here is where things get really wild. This is the secret that makes these continuous groups so incredibly powerful. It's the moment where the abstract rules of math actually transform into something you can see. A group with all these infinite, continuous symmetries is called a Lie group. And what's so special about it? Its incredible power is that the group itself, that whole collection of infinite symmetries, can be visualized as its own smooth, geometric shape. Think back to the frisbee. If you could actually map out every single one of those infinite rotations, what would you get? You'd get a perfect circle. The rules of symmetry and the shape of a circle become the exact same thing. In this case, the circle is the Lie group. Okay, so you're probably wondering, how in the world do mathematicians work with these complicated, curvy shapes that have infinite points? Well, they use a truly genius shortcut. Just think about this for a second. We all know the Earth is a sphere, a giant curve, but when you're just standing around on it, the ground looks flat, right? That's because you're zoomed in so close that the curve just seems to disappear. The same exact idea works for these groups. By zooming way, way in on a tiny little piece of that Lie group shape, mathematicians can basically pretend it's a simple straight line, a tangent line. And this simplified straight line version is called a Lie algebra. It's this amazing trick for turning a really hard problem about curves into a much, much easier one about lines. And this shortcut is really the whole point. As MIT mathematician David Vogin explains, it lets mathematicians take these incredibly complex ideas and study them using one of the most basic tools they have, linear algebra. It's a huge simplification. So now let's zoom back out and get to the real payoff. Why does any of this abstract math actually matter? Well, because, amazingly, it turns out to be the fundamental language of the universe itself. It turns out that all the fundamental forces that run our world are actually defined by these continuous symmetries. This means gravity, electromagnetism, and the nuclear forces that hold every atom together can all be described perfectly using the math of Lie groups. But the connection gets even deeper. Back in 1918, a brilliant mathematician named Noether discovered a truth so profound and so beautiful that it completely changed how we see the physical world. Her theorem proved this incredible one-to-one link. If a system has a continuous symmetry, one of these Lie group symmetries, then some physical quantity has to be conserved. It's not a maybe, it's not a coincidence, it's a mathematical law. And just look at the mind-blowing results of this. The fact that the laws of physics are the same now as they were a billion years ago, that's a symmetry in time. And Noether's theorem tells us that's the very reason energy is conserved. The fact that the laws work the same here as they do on the other side of the galaxy, that's why momentum is conserved. It is a truly profound connection.
So in the end, symmetry isn't just about aesthetics or making things look pretty. It is the deep structural rulebook that tells our universe how it has to work, from a simple triangle all the way to the conservation of energy. It's the hidden language that makes everything tick.
This just goes to show you that some of the deepest truths about our reality are really just expressions of a simple, elegant pattern. And it leaves you with a really exciting question, doesn't it? What other foundational symmetries are still out there, just waiting to be discovered?